Welcome back, AP Chemistry students, to Unit 8, Acid-Base Chemistry. Today we will be talking about Unit 8.2, the strength of acids and bases. Now, since we talked about acids being some sort of substance placed into solution that produces hydrogen, ions, and some anion, most acids set up some sort of equilibrium. So, the strength of an acid deals with that equilibrium state. How many ions do you get for each mole of acid placed into solution? So it's all based off of that dissociation. If an acid breaks up completely into solution, it's known as a strong acid because it's a strong electrolyte. Remember from our unit on bonding that an electrolyte is a substance that can close a circuit, allowing electrons to flow through it, so a light bulb would light up brightly. Strong electrolytes produce lots of ions in solution. So a strong acid is an acid that breaks up completely when placed into solution. The good news is there are only 6 strong acids that you need to know. These are the halides with the exception of fluorine, so hydrobromic, hydrochloric, hydroiodic acid, as well as nitric, sulfuric, and perchloric acid. Those are the 6 strong acids that you have to know. And unfortunately, you have to memorize that these are strong acids. That means that for every one of them that you place into solution, you will receive 1 hydrogen ion. They break up completely. So for example, nitric acid, when placed into solution, does not really set up an equilibrium. It simply breaks up into hydrogen ions and nitrate ions. It has a Ka value that is way bigger than 1. The same could be said about sulfuric acid. Sulfuric acid will break up into a hydrogen ion and the bisulfate ion. Keep in mind, acids only donate a single hydrogen at a time. So when we say that sulfuric acid is a strong acid, we mean that it gives us that 1 hydrogen very readily. The second one will come off eventually, but that's a common ion question, and we will deal with it when we get there. Perchloric acid is listed as a strong acid, but others in the chlorate family are not, right? Like chloric acid or hypochlorite are not listed as strong acids. So what is it about perchloric acid that makes it strong but not its cousins? Well, it has to do with the fact that on oxyacids, the hydrogen is linked to the oxygen of that oxyanion. Oxygen is an electron hog. It's more electronegative. So it attracts the electrons in that bond with much greater force, leaving that hydrogen, that proton, largely out on its own, with very few electrons ever orbiting it. The more oxygens you have, the more this effect is magnified. So when you have more and more oxygens, when the electron density of that oxyanion increases, this bond becomes weaker and weaker. And so it requires less energy to remove that hydrogen from the oxyanion. Now, strong bases are the same way. A strong base will dissociate completely into solution. Luckily, again, there are only a handful of strong bases that you're required to know. These are any group 2 or group 1 hydroxides, right? So any group 1 or 2 metal with hydroxide will be a strong base. So for example, sodium hydroxide is a very strong base. It has a Kb value that is way bigger than 1. So it heavily favors the production of those ions. There are some exceptions for magnesium hydroxide and beryllium hydroxide are both not really considered strong. because they dissociate, but their percentage they dissociate is a little weird. So generally speaking, the AP exam is going to avoid these two because it kind of coin tosses depending on who your professor is, depends on whether or not magnesium hydroxide and beryllium hydroxide are considered strong. But again, general speaking, any group 1 or 2 metal hydroxides are considered a strong base. Now, when something's a weak acid or a weak base, that means it does not dissociate. So in the example of an acid, it sets up an equilibrium where the acid could break up into hydrogen ions and the anion, but more often than not, it stays together. These heavily favor staying together. They'll have a Ka that is less than 1. And usually it's pretty substantially less than 1. Most of them will stay as their molecular form and not form ions. This causes them to be a weak conductor of electricity. Now, they will conduct electricity. They are a weak electrolyte. All acids are electrolytes, but the vast majority of them are weak electrolytes or weak acids. So when we say an acid is strong or weak, we are not talking about how dangerous it is, right? We are talking about how well it conducts electricity. Hydrofluoric acid is a weak acid. However, it is extremely dangerous. Getting a single drop onto your finger will cause you to have your hand amputated, and 5 milliliters on your finger or hand will cause your entire arm to be amputated, as the fluoride ion readily leaches the calcium out of your bones. You will die very quickly if you are not treated for that type of poisoning. So again, the strength of an acid just deals with how well it conducts electricity. Now, if something is a strong acid, it means that it has a very weak conjugate base. Because if it's a strong acid, it heavily favors the donation of those hydrogen ions. And that means the anion form must be a very weak base because this forward reaction is so heavily favored. In the reverse, if something is a very weak acid, that means that the forward reaction is not heavily favored. The reverse reaction is favored. A weak acid has a very strong conjugate base. So they kind of run opposite one another. If something's a strong acid, it's usually a weak conjugate base. So when it comes to acid-base equilibrium, they do set up an equilibrium, meaning they have an equilibrium position. That ratio of products to reactants that we learned about in the last unit, we are going to continue here. The only difference is now that we are talking about this ratio in terms of an acid or in terms of a base. Literally the only difference. So we can talk about how heavily favored the reactants or products are using these values. They are still calculated the same way, that it is products over reactants. But notice that if you are dealing with an acid-base reaction taking place in aqueous medium, we do not include the water. Remember, water is so heavily concentrated that it is not part of an equilibrium expression. So if we're asked to write the Ka for an acid or a base, it's just a matter of writing that equation and then filling in and then writing our equilibrium position. So for acetic acid, if we were to write the dissociation of acetic acid, we could simply show that acetic acid donates a hydrogen, separating it from the acetate ion. That's one way we could write this, simply write the dissociation. Or if we wanted to write the full out expression to show the conjugate acid-base pairs, we might write it this way. Both answers are synonymous, showing the water or not showing the water. So since both will work, I'll put both up on the screen. In either case, writing the equilibrium position is going to be products to reactants. So Ka is going to be our products, the hydrogen or hydronium ion concentration times the concentration of the acetate ion over the concentration of our reactants. Remember, water is not part of an equilibrium expression. So there is the Ka. Both answers are synonymous. Both answers are correct. If the question specifically wanted you to show how it reacts in water, the top answer is the better of the two. However, they both are valid answers. For letter B on example 3, there is unfortunately only one way to write this. In order for you to show how ammonia acts as a base, you have to show it reacting in water. So ammonia reacts with water to form ammonium and the hydroxide anion. Again, that's because the ammonia can pull the hydrogen from the water to make hydronium. So, to write the Ka for this expression, it's going to be products over reactants, and again, while water is part of this reaction, it is so heavily concentrated it will not be part of our equilibrium expression. And since we make hydroxide, this is a Kb, an equilibrium position for a weak base. So what does Ka and Kb mean? Remember, it just deals with equilibrium position. If you have a K that is very large, that means that you favor products. So that means that you favor the dissociation. So when Ka is very large, that is a strong acid. If Ka is weak, if Ka is low, very small, that means you favor reactants, meaning that most of the time they stay together. So that would be an example of a weak acid or base. And again, we can use these to discuss whether an acid makes lots of hydrogen ions or very few. So a Ka that is very small makes very few hydrogen ions. So for example, phenol is a really weak acid. It produces very few molecules of hydronium, while something like hydrogen sulfate or bisulfate would be relatively strong in comparison because it would produce more hydronium molecules. Keep in mind, if something is an extremely weak acid, that makes it a strong base. So phenol might be a very weak acid. It is a fairly strong conjugate base. So for example 4 in our packet, we were asked to rank the following in terms of their strength as a base. So if something has a very high Ka, it must have a very low Kb, meaning it must be a very weak base. And since hydrochloric acid here is a strong acid, it must be the lowest on this scale. Next up would be the next up in the run. So we see nitrous and hydrofluoric acid. So which one of these must be the weakest the next weakest? Well, 7 is bigger than 4, so I would probably say that 7 would come next. So hydrofluoric, or the fluoride ion, must be the next strongest base. Then the nitrous ion. After that, we get to 10 to the negative 10th or 10 to the negative 7th. 10 to the negative 7 is bigger than 10 to the negative 10th, so water would have to come next, and that only leaves the cyanide ion as the strongest conjugate base on the screen, because it's the weakest conjugate acid. So in your packet on page 16, you have already written the dissociation for these acids. So for sulfurous acid becoming hydrogen and the bisulfurite ion, you're asked to write Ka. Remember, it's just products over reactants. So the concentration of hydrogen times the concentration of the bisulfite ion over sulfurous acid's concentration would give you Ka. Do the same for all the others, and that will be the end of Unit 8.2. I will see you next time where we talk about calculating pH from those Ka and Kb values.